So, like we said before, this past weekend was CSAW qualifiers. And one of the challenges in there was a problem that I wrote called LittleQuery. And for those who don't get the joke already, Google has this service called BigQuery, which is their enterprise data. Just dump all of your logs and everything into it, and they'll do scan through terabytes of data in a couple seconds and do like big analytic queries out of it. So we're LittleQuery. We're going to process all your enterprise big data with JavaScript. We're going to do it. We're going to do it in this isolated VM on dedicated hardware, giving you great security. And it's just please don't sue us, Google. So this is the site, and first thing first, let's just do exactly what we just talked about. Let's just look at source. So, okay, this is interesting. There's an HTML comment. There's a reference to this API endpoint. Okay, this is going to be useful later. Let's, open that up in a new tab and just keep an eye on it. But otherwise, it doesn't look like there's really anything else besides HTML. I also actually dropped it in robots.txt as well, as we just talked about, just so that if competitors didn't do one, because you need to find this to be able to proceed with the challenge at all. So I needed to make sure that the people playing would actually find this API endpoint somehow. And if you go to /API, I even left directory listings on, so you would see exactly that there is one API endpoint, DB Explore. So at this point, okay, it's pretty clear what we need to do. It's something that has to do with this endpoint. The only other option is to try and sign in, and if autocorrect wasn't there because I wrote it, we wouldn't know anything. We wouldn't, we don't have anything. We can try putting semicolons in both. We don't seemingly have quick SQL injection. So not a whole lot there. One thing to note though, why it's worth just even mashing on the keyboard to try these. If you look really quickly, let me zoom in on this, watch what happens to the password field right as I click sign in. Did you see how it extended out really quickly before the page loaded? Okay, so that's weird, right? That doesn't normally happen on most websites. So let's again go through source, and we'll see, presumably that meant some kind of JavaScript, right? You need to, JavaScript is basically the only way to run client-side code on a website. So if we look, okay, so we can see we have kind of standard libraries. I guess just for people who haven't done a lot of web dev before, anytime you see like a CDN involved, so CDN.js or Google APIs or anything like that, that's all static code. You're not going to find, things to do with the problem in there, right? This, however, login.js, this is local to the website. So this is, okay, what's this code doing? And we find that in this case, let me make sure you can read that. Oops, there we go. Where when you click on sign in, we're grabbing the password out of the field, running it through SHA-1, and then basically replacing the text field with the result of the SHA-1. So we're doing client-side hashing of the password. This is sort of weird. For people who haven't done web dev, normally all password hashing occurs server-side, because when you do password hashing client-side, you potentially have some issues that server-side hashing avoids. Primarily, when you're doing hashing server-side, you normally include what's called a salt when you hash it. We'll get around to this a lot more in depth when we do the crypto stuff later on in the semester. But in short, that salt is there to just prevent some really common dictionary attacks, which are basically like, let's just pre-compute the entire SHA-1 of every word in the English language and just see if any of those match the hash that we get. So when you salt something, that means there's no way it can just be an English word because you have some random data beginning or end or somewhere in the middle. So it basically removes the ability to do those kinds of texts because we're hashing it client side. In our case, though, this also means something more significant, which is assuming they aren't hashing again server side, this is potentially, we can potentially bypass the authentication flow because we don't need to know the password to be able to log in. We just need to know the hash of the password to log in, right? Because the result of this SHA-1 is what's actually sent to the server. So it's all it's ever known about how to log in. It knows it receives a SHA-1 and then does some comparisons on the database. It's possible that they could hash it again. However, for CTFs, this is weird at the very least. So it's something to keep in mind. So we'll keep this open. And if we now go back to the DB Explorer endpoint that we found earlier, this is being very nice to us. It's telling us exactly how we need to talk to this API. In this case, it's saying we must specify mode is schema or preview. So if I don't know how well you can read the URL up top, but if we do mode equals schema, we can now see, okay, it looks like it's giving us a listing of databases in this case. So, okay, what if, is there any way, I wonder, since, this is supposed to be a service that allows you to query off of data, we need more than just the database to be able to form queries, right? We need tables and we also need columns. So let's see, is there a way that we can pass the database? We know there's a database called LittleQuery, so let's try and pass db equals LittleQuery, and we get tables back. If you had tried database equals LittleQuery, you wouldn't have gotten an error, but it just would not have progressed. So the idea with this, again, coming from the challenge writer, is I even abbreviated DBs. So in theory, you'll try DB equals soon enough. And then we find we have tables. So let's try adding a table equals user. And now you can see it's given us basically all we need to construct queries against the database. We have a list, we have our database, we have the table in the database, and we have the columns in that table. It even tells us what type they are. The idea behind this, again, is that in the query editor, whenever we get around to logging into it, that this would be presented to the user as basically saying, here is your available data sources, and so you can really quickly see what data you have, and how to access it, basically. This is kind of getting into the meta of the challenge, if you will. So, okay, we've basically hit an end at this point. We can't. It doesn't really make sense to really specify anything else. We already have essentially the most fundamental unit of what a schema can be. Remember, you don't have actual data in the schema. You just have the description of how the table is formed and how the tables in the databases are formed. So we can try saying like and column equals UID or something, but we'll see. We get the same thing back. And at this point, again, we've hit the natural end of this point. So if we go back to DB Explorer itself, as you'll remember, there's also this mode preview. So that sounds good. It would be very nice if we could preview the database. Again, the mentality behind this and like the meta of the challenge is you want to be able to theoretically, maybe hover over the table to see what kind of data it is. If there's some ambiguity about how a certain field is stored or what's in a field, you could hover over it and see a sample of the data set. So in our case, again, the end objective is to log in, right? So that's the only thing you can do from, that's the only thing that you can do from the main page. So if we can preview the users table, essentially, that would be a very good thing. So if we go mode equals preview, again, it's incredibly helpful. It says you must provide DB and table to preview data. So if we try and specify DB equals LittleQuery and table equals user, again, as we saw earlier, what we're wanting to do, it says database LittleQuery is not allowed to be previewed. So, okay, it's not that easy. The challenge here is not just navigate around an API. We have to actually exploit something here. So at this point, does anybody have any ideas about what we might be able to do to advance through it? To advance to potentially leaking the database, leaking the users table to log in. Anybody? Good. Yep. Can we do what? So yeah, so before we can do anything really useful with hashing being done client side, in theory the end goal, the end objective of that is you don't need to know the password itself to actually log in. You just need to know the hash. So we can't do anything with that quite yet because we still don't know what hash it's wanting, right? Did you have a hand or?
Yeah.
Yeah.
I was saying you might try to insert a single quote or
Good. Yeah.
to one of the parameters. See if you can get
Cool. You want to do that in the preview mode or in schema mode? But we can try both. Like schema. Okay. So let's try. We'll go back to our table equals user. Let's try just dropping a single quote into LittleQuery, and it doesn't error, but we don't get any columns back. So at this point, we can assume that the query itself went through to MySQL, and MySQL just didn't return anything, right? Because otherwise, if it was a syntax error, we would have gotten a 500, or if I had caught the exception, we would definitely not be returning blank. We would be returning some kind of, this is malformed, stop doing whatever you're doing. So nothing there. And we get the same thing with table user. Maybe if we have something like, in theory, imagine the actual code behind this. Perhaps it's like some kind of nested if, where if you just have database specified, you run one query. If you have database and table specified, you have another. So let's just try the outer layer of that, where if you just have the database specified, but unfortunately that still doesn't work. We still don't get any data back, and there's no error. So we can assume pretty well that it's not the error. The quotes are either being stripped out or it's being properly escaped. If the quotes are being stripped out, perhaps we can try throwing a backslash in, but that doesn't appear to be doing anything either. A space or something also doesn't really do much. So this doesn't seem to be super fruitful. So let's now try the same kind of thing. The same kind of thing on the preview mode. So this time, if we throw a single quote in, we get something different back, though. We get something that says LittleQuery with, you'll notice it's escaped, but that doesn't exist. This is much different than just returning nothing. And what we're about to see next is, I think, probably where most people got stuck up in the challenge who are playing over the competition. Does anybody have an idea what we can do here? We know that, I know you do. So we know single quotes are being escaped. Yeah.
Or backslashes being escaped.
Okay, so we can try if backslashes are. And yeah, so unfortunately it looks like those are also being escaped, but good, yeah. Backtick, all right. Okay, that's interesting. We don't see a backslash in front of that. So this is potentially interesting. Let's try, if you remember back from when we talked about SQL, I think this was probably first week, you can specify a specific database and table to use if you're in one database and you want to reference data to another database, you can do this database.table syntax. And these backticks also are what MySQL uses to say this isn't a string, but anything encapsulated inside of this is essentially a string literal, but should be used for this database and table indexing. So we can see that's not being escaped for whatever reason. So that's this is potentially very good. Let's try and recreate this LittleQuery.user thing. So you can see now I basically injected this part. And so you can see, okay, so we've now recreated what we would expect to see in the statement. We have, presumably, it is select star or something along those lines from this LittleQuery.user, but we still have all this extra data. at the end. So what's also nice about this is that we can actually check to see, you know, are spaces escaped? No. Are dashes escaped? No. So we can potentially inject off of what we have here, because if we basically have all of the parts that we need at this point. We have a way to specify data. So if we try and end that, you can see very clearly now where exactly we're injecting. And now if we do that, that looks better. For anybody who can't see, what we just did was terminate the query. That's not actually needed. And then we just do the exact same thing that we've been doing for basically all of SQL injection, space, dash, dash, space. And so what this is effectively doing is, if we go back, we're going up to here. So we have, presumably the query looks something like select star from some escaped db dot some escaped table. And then, presumably, maybe we have like a limit after that because it's just supposed to be a preview. But regardless, this is the basics of the query. So if we have this escape DB that's not actually escaped for these backticks, we can just do classic SQL injection, and there's a hash. So this is where we get to why client-side hashing is potentially dangerous, because now, if we take this hash, well, let's just see what happens if, instead of just putting that as our password, let's see what happens if we put it there. I believe in the description I specifically said that you need to log in as admin, but regardless, admin is always a fair user to try and log into as, in case it's not clear by now. And let's also just actually disable JavaScript entirely. If we go... Actually, I honestly forget how to disable JavaScript on a web page where...
Back in the other window.
Mm.
Yeah, and then you click on where it's not secure, you click on that.
Ah.
Yeah.
And then JavaScript block. Okay. Yeah, so reload, there we go. Okay, so admin, let's enter our hash that we got. Aha. There we go. So we are now logged in, and since the hashing is done client side, and the server didn't appear to do any additional hashing, we can now, it's called passing the hash. It's pretty obvious when you think about it this way of like, well, yeah, the client's normally passing the hash to the server, but it gets interesting when you have, like, from a server-side mentality, you see, well, the password isn't the password. It's already been, messed around with, so it's irrecoverable. So why do we need to do anything more to it? However, this is forgetting the fact that now, if that hash is ever leaked, that's all that's needed to authenticate. If you do the hashing server-side, you actually need the original password such that the hash of the original password and the stored hash match, which means you now have to brute the password against the known hash, and that takes a lot more time versus just, here is the hash, now you are logged in. So yes, the joke in here, the flag is maybe it's time for real escape string, because funny enough, all of the escaping that was not done, that is passed through MySQL's real escape string. That is what PHP considers fully escaped, because of course that is supposed to be used to escape strings, not these literals that are used for database and table names. Yeah.
What was the command that you used to get the data?
Right. So if we... Is that glitching out? No, okay, that's just saying on my display. So if we set our database to this, which, again, it should look very familiar at this point, where we have basically the end of the database that we know from our like schema listing mode. We know the table of user again, and so we're just recreating the syntax that SQL uses for having backticks around database and table name literals. In fact, I don't think those are actually even needed to do this. Yeah, so you can just do backtick database name backtick dot user. This is again presumably just select star from maybe there's a limit after it, but again, we can just end the entire query with a comment, and there you go. That's, we've now leaked out UID, username, admin, password, which are the columns that we saw from earlier. So yeah, again, this is another common-ish thing with PHP, where functions do exactly what they say they do, right? They aren't going to escape more than they do, which means even if you have real escape string, you need to make sure you're just using that to escape strings. It will not work for other things, in this case the database literals, but it's a fun trick nevertheless to know that real escape string does not escape literally anything that you need to do for SQL injection except basically just quotes and slashes. That's almost all that it really gets rid of. So,
while we're here, do you want to show them some big data analytics?
Oh yeah. So, sure. The second part of this challenge, let me re-enable JavaScript just so I can, oh, come on, whatever, I'm already logged in. So, this is going to be, do we want to show like the full exploit or what?
Yeah, sure. Okay. But, like, explain what.
Yes,
what
yeah.
all this
Right,
is.
so let's talk about what runtime.js is. So, runtime.js is the result of, I forget their name. Somebody thought basically, okay, we have JavaScript and we have a pretty fast JavaScript interpreter, V8, which is what Chrome uses. And it's memory safe in theory, right? If we assume that the interpreter does not have bugs, it is basically impossible to like do bad things with JavaScript, right? So the idea with this is, let's take JavaScript, let's strap it on top of a really, really thin kernel that basically just has native C implementations for just the very basics of bringing the system up and talking to hardware. And then that's an OS, right? We have the very, very thin kernel layer and then a full JavaScript environment where you can code whatever. And the premise behind this is basically, everybody, if you've done development for front-end with front-end JavaScript or back-end JavaScript with like Node stuff, you can now drop this into literally just a VM that all just runs JavaScript. And there's no PHP to learn, there's nothing else. You just take basically your existing code from like Node.js or something, you drop that into runtime, and you're now just running on bare metal. So this sounds odd, right? But relatively okay at first glance. So let's take a look at runtime's repos. And yeah, they basically just tell us, okay, you just set up this thing with npm, and eventually you'll get a QEMU VM that starts with your code running and all seems well. And sure enough, this is definitely JavaScript. We can console.log things, and if we hit run in about 20 seconds or so, we should see our output pop up in the terminal output below. And eventually, this was supposed to be a little bit more real-time. However, for some reason, I'm not exactly sure what changed. I believe this worked locally, but regardless, there we go. You can see hello from runtime.js, and this is indeed running inside of a QEMU VM runtime.js. So this is going to be, what we're about to do is a bit of a sneak peek at pwning and also just in general weird OS stuff, in case you haven't taken OS yet. So since we don't have 5 hours to spend on this challenge, we're going to kind of blow through a couple things. So after a couple hours of reversing runtime source, you will find that they actually expose this dunder syscall object from V8, which lets you do essentially syscall things. It lets you do relatively low-level OS operations. One of them, I believe, is called get memory, or it's get resources or something like that. We'll look at the exact demo later, but you can essentially get a list of the system resources, and then in this case, there's one that's called, I think it's called get memory range, and this gives you a handle to basically a JavaScript buffer with these physical addresses just mapped in. So if you access the result of this array, item 0, that is literally just reading from physical address hex 1000 in memory. So this is a bit weird. This is not supposed to be able to be done from JavaScript, right? We were told that this would be memory safe. However, if we can read and write to arbitrary places in memory, that does not sound memory safe. So if we let me open up the sample that I had. Quals run funtime. So this was the sample solution that we provided. Basically, here's our get system resources call. And we'll kind of walk through this as we go. I realize that's probably hard to read. Let me make this not night mode if I can figure out how to change that. Does anybody know TextMate very well? / where I can just hit don't do dark colors. Theme, maybe? View theme. What is the default? Dawn. Is that sort of readable? Okay. So here's our call to the get system resources that I saw earlier. And this basically just returns, like we said, a JavaScript buffer with these physical addresses kind of backed in the array. So if you write to offset 0 of this mem array, you'll be writing to the physical address hex 1000 in memory. We have a quick helper function, which because the integers that we're dealing with are 32-bit, we basically need to say, given an actual memory address that we want to poke at, how can we get the index of into mem, since it's mem is the uint8 array, so each index, bless you, each index is a single byte, but most numbers, it's a uint32 array, so each index is 4 bytes, and we're going to want to add, if we're going to want to access particular bytes to poke at them. So the way V8 works at its core, and part of the reason why it's so fast, is that it does something called just-in-time compilation, or JITting, as it's commonly known. And basically what that means is when you have a function in JavaScript, in this case we just have a function called a that literally just returns the constant 1234, hex 1234. When you have this and when you first run it, V8 will take this and actually compile it into native assembly for your machine, and then we'll run that native assembly. So as soon as it's compiled it this first time, it no longer has to know about the actual JavaScript. It just knows that there is a function at this address, which is the native code to run this function. So this is why it's so fast, because you do this once, and now anything that's like in a tight loop is now just hitting actual assembly. So it's pretty darn fast, right? And so what we do here, the way this exploit works, is we take basically all of memory that we care about, and we actually look to see, since we ran this function, we'll know it will have been compiled already, and we look for specific assembly instructions that, I forget what I actually did to find these, excuse me, I believe, I think eventually I just kind of like, I set a breakpoint in here somehow and then just stepped through until I saw that actual code being run. Or I might have actually just scanned for the literal 1, 2, 3, 4 in memory, I forget. Regardless, basically, it's JIT, and it's going to do the same thing every time, right? Where the exact address that it ends up at could change, but the actual assembly that we care about is going to stay the same, because the function's the same. Why should it change? So we scan all of memory for the beginning of this function. We mark that, and then we literally just overwrite the compiled function with our own shellcode up here. And so what that means is that where V8 thought is, the implementation of this is actually our own shellcode. So whenever we jump to that function again, our own shellcode will be running, instead of what V8 thought was the implementation of return hex 1234. So we overwrite that, and then we call this function again, and now our shellcode's running. So what does our shellcode do? So the way you beat this challenge is by reading a flag at a given location in physical memory. I believe it was hex DEADBEEE. hex dead beef. And so it's relatively simple assembly. And you'll learn more about all this. It will be simple at some point.
We're going to be starting a much more basic way to look at this next week. So don't feel lost. We're going to start from like the first 2 lines are going to be like an hour of next week.
So in
Maybe
short,
less, maybe a bit less.
maybe probably a little bit less. So, you know, most of you should, I believe or in theory, everybody had to do the basic assembly challenge that we gave to get into this class. If not, don't quite know how you got in, but whatever, you're here, so, you know, whatever. You made it this far. So, basically what this is doing is we're taking this constant of DEAD A0008B, moving it into a register. And then we're taking that value and we're storing it into this specific location in memory. Anybody who's not in the lab, anybody have any idea what we could be setting up here? I'm curious. If you've taken OS, you should know this. The address basically has nothing to do with it, but this address might seem a little bit suspicious given that we're trying to read from dead beef. Notably, why is that not just dead beef? And what could it be instead? I'm not expecting anybody to know this, I'm just curious if anybody does. Guesses? Yes?
Is that like a return point?
No, but good guess. Max, yeah.
Just like trying to read like a large portion of memory.
Almost. So one issue here is that the address we're trying to read, notably, is above the limit of 32-bit addresses. It's past hex FF, 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 FF. So what that means is, you know, the whole reason we couldn't have just gotten this memory range to that address in the first place is that runtime, for whatever reason, just limits you to 32-bit addresses, physical addresses. Sort of makes sense, but you know, that now explains why we can't do it there. But any other ideas as to what that address could be? Again, I'm not really expecting anybody to know, but okay. So basically, what we're doing here is we're actually adding our own page table entry. For those who've taken OS, that'll make a lot of sense. For those who haven't, basically, when you have, there are 2 types of addressing in most architectures nowadays, basically all of them. You have virtual addresses and physical addresses. Virtual addresses are what what you do, basically it's how you interact with everything, right? Virtual addresses can be the same between different processes. Usually, you know, there's a couple common addresses where basically all, at least Linux programs will land. And that's what everybody's familiar with. But to be able to read, and basically whenever, in all of the contexts that matter right now, we can only read from virtual addresses. We don't have an easy way to read from physical memory. However, the flag is way up in physical memory. So we need to basically say, okay, this virtual memory, how does that correspond to an address in physical memory? And this is what page tables do. Basically what we're doing here is we're just adding an entry that says, for a specific offset, in this case, if you try and access, I believe it's, it's this. If you try and access 0x301 something, it will map that to physical address DEADA plus whatever's here. These 2 bytes, or this byte is the only one that actually matters for the page table that we need right now. So we add this page table entry, and then this loop, as complicated as it looks, literally just goes through each character and prints it out to the terminal. We set up the address that we want to read from. We say out, long story short, 3F8 basically just says write it out to the serial port, and then we just loop over everything, dereference the address to get the value at that byte, spit it out on serial, increment, repeat. And that's all. And what's funny is I was actually intending to do a bit more with this part of the challenge, because does anybody see a big step that could have been avoided, seeing that all we needed to do this was write to write to an address and then read from some virtual addresses that are notably below the 32-bit boundary? Yeah?
Yeah, you could have done that with the
with this. Yeah. Yeah. So most of the teams, I think all the teams that solved it actually didn't end up needing to do any of the shellcode stuff, but it's fun nevertheless.
I think RCI got shellcode running.
They did? Okay.
But I know the other two didn't.
Yeah. So regardless, this is, I guess, kind of a way to transition from the web stuff that we're doing with the first part of LittleQuery into RE and Ponables, which is basically going to be the next 7 to 8 weeks, more or less. Yeah, so it's basically 8 o'clock. I think from here on out, the rest of the class, if you haven't finished the homework yet, we'll be around if you want to ask questions. If you've already finished or if you don't want to stick around, feel free to bail. Otherwise, yeah, or if you have any questions about this, feel free to ask. There's no reason to really know this right now, but we thought it would be fun. Why not? So, yeah.
I
Yes.
also want to point out that actual web browser exploitation doesn't often look too much more complicated.
That's actually a very good point.
You've got a read-write primitive.
Yeah. That's a very good point. Once you if you're actually trying to exploit Chrome or something like that, this is not all too different from what you would see in the real world. So, anyways, yeah. Feel free
If you're
to.
interested in working at a large 3-letter agency who pops Chrome on random pedophiles' computers, this type of thing is what you're going to be doing.
Yeah.
Um,
But yeah, so feel free to head out now if you want, or stick around for homework, Q&A, questions about this, basically whatever. If you guys are headed out, see you next time. Homework will be